Hello everyone and welcome to this first lecture on chaos theory. Now what we are going to do in this lecture is really lay down the basics of discrete time dynamical systems. As I mentioned in the intro lecture, we are going to look at chaos theory from the perspective of discrete time dynamical systems. Now, the primary motivation, at least for me as someone who studies dynamical systems, is that these discrete mappings can be seen or understood as Poincare mappings of a continuous time process, okay? So again, if you have not reviewed my continuous time dynamical systems lecture series, I would go back and I would look at that, at least refresh some of your memory up to and including that Poincare mapping section video. From here, we begin with the basic process. We are going to consider a function which will for now considered to be a one-dimensional function, and using this function we will use it to generate a sequence of real numbers. Okay, so again, this is sort of the basics of calculus. A lot of calculus is driven by sequences and series if you learn a little bit more advanced calculus. So essentially what this says is you give me a number, I put it into the function, I get another number. And what this is this generates a recursive process, right? So if you're coming at this from the perspective of programming, this is essentially a loop procedure, right? It's a recursion loop. You can implement this with a for loop. You just need to tell me where I start. So this generates what we call an orbit. And an orbit comes from an initial condition x naught, and then I can use this to get the next point x1, which is just f of x naught, and then I can use that to get the next point, which is f of x1, and so on and so forth. And I would call the whole orbit here this infinite sequence of numbers that just comes from taking the previous element of the sequence and putting it into the function f to generate the next one. Now, of course, I can do this ad infinitum, right? Every step of this just gives me a real number. I can always evaluate this. This thing doesn't blow up in finite time, right? This is a genuine infinite series or sequence, sorry, of real numbers, okay? Now, most of what we are interested in is understanding where this thing goes. That is the primary occupation of dynamical systems. We talk about limits, we talk about limiting sets, limiting objects, all of these kind of things. But before we talk about that, if f is invertible, we can also talk about a backwards orbit, right? So if I was able to take an inverse of this thing, I could say that the pre-image of my initial condition is given by applying the inverse here. Similarly, the pre-image of the pre-image is given by applying the inverse again. And if f is invertible, this actually defines a bi-infinite sequence. So we can think of the elements of my sequence as indexed by the integers. Now, as we will see, in a lot of the really simple sort of interesting cases that we are going to study in this lecture series, we will not have invertibility, right? So one thing that you can carry with you through this is simple chaos is a process of stretching and folding. You can think about it as making dough. You stretch out the dough, you fold it back on itself. You stretch out the dough, you fold it back on itself. And that process of folding actually means that your original mapping is not going to be invertible, right? Because you're taking one piece of dough, stretching it out, making it twice as long, and then folding it back on itself. So the original dough has two layers now. So a lot of the time we're not going to have invertibility, but it is worth thinking about. You can have these bi-infinite sequences as well, and then you can talk about double limits, right? Going to negative infinity and going to infinity. Now, another critical important concept here is that of a fixed point. Okay? Now, fixed point, equilibrium, there are many different names for these things. We're going to use fixed point, and that comes from the fact that a fixed point is a number that you put into this function and you get that function back, or you get that number back, okay? So it comes from solving this equation right here. This equation is saying if I put a number in, I get the exact same number back. And if you think about what happens here, then that means that if I started with this fixed point as an initial condition, my sequence is constant, okay? I put it in, I get it back. I put it in, I get it back. I put it in, I get it back. And constant sequences rock, right? They are one of the best things that we can work with because the limits are easy. We can talk about limits of constant sequences. They're just the constant. So these fixed points play a critical role in our understanding of these discrete time dynamical systems. Moreover, we can talk about periodic points. So periodic points. And periodic points are going to do this. They are going to say that if I go forward by p steps into the future, this is the same as where I started. Now, if we think about how this orbit actually works, if we just do a little bit of scribbling here for a second, right? It essentially tells us that xn is the nth composition of f with itself, right? So this is f of f n times with the initial condition. And so essentially what this piece is right here, this is saying that it is a point that comes back to itself after p applications, okay? So this would be an example of this would generate an orbit or a sequence here that repeats every p entries of the orbit. In particular, we would talk about the prime period, so you can feel a little bit of maybe number theory starting to show up in here. The prime period of a periodic point is one which is the smallest value of p that you come back on yourself. So think about this example, okay? A fixed point would be a sequence that looks like 1, 1, 1, 1, 1, 1, right? It's just a constant sequence. So a fixed point, its prime period is 1. But imagine you have a sequence that looks like this. 1, minus 1, 1, minus 1, 1, minus 1. Then it takes 2 iterates, or 2 steps through the orbit, in order to repeat. So we would say the prime period of that periodic point is 2. If it went 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1, that is a period 3 orbit, prime period 3. Okay? So let's do an example. Okay, here's my example. F of x is equal to x cubed. Okay, very, very simple function. I mean, we see this, it shows up in sort of calculus. It's one of the first like complicated, semi-complicated functions we've learned. So then the fixed points of this thing, so let's look at it like this. We have x is equal to x cubed, which tells us that there are 3 fixed points, 0 and plus or minus 1. If you put 0 plus or minus 1 into this function, you will just keep getting those over and over. So there are 3 fixed points to this function, whereas we could look at another example. If we look at x squared minus 1, okay, in this case, then we have to solve this function, which, again, if you're coming at this from number theory, you might actually know this equation. The roots of this thing are the golden ratio and its inverse. So let me just remind myself. this is x is equal to 1 plus or minus the square root of 5 over 2. Okay, so its fixed points are the golden ratio and its inverse. But also, I'm going to leave this for you to check. So also, x equal to, let's see this, 0 and minus 1 are period 2 points. And what I mean by that is if you put x equal to 0 into this function, you get minus 1. And then if you put minus 1 into this function, you get 0. So you get, if these lie on an alternating sequence, 0, minus 1, 0, minus 1, 0, minus 1, 0, minus 1, etc. And that means that they are periodic points, right? They lie on the same orbit. And the sequence repeats every 2 elements. Okay? So this is really sort of the fundamentals of this. Now, related to the study of dynamical systems is another example of functions in one dimension that we're going to look at. We're going to let S1 be the unit circle. Now, of course, if you're coming at this with a knowledge of topology, you know that this can just be, this is diffeomorphic to just any closed curve in any dimension, okay? But essentially what we're going to look at is we're going to let theta be the angle on S1, okay? So we can parameterize this entire manifold just by the angle that you're at along this thing. And of course, we're going, this has a periodicity, so we're going to set theta is congruent to theta plus 2 pi k for all k and z. Okay, so when I talk about, this is just the sort of basics of whenever I'm talking about, you know, the unit circle, I'm always going to parameterize it by its angle. And of course, we're going to say it has a period of 2 pi here. And then here's what we're going to look at. We're going to look at a function from the circle back to itself by f of theta is equal to 2 theta. This is what's called the angle doubling formula. So every time you have an angle, you double it. Okay, so if your original theta was pi radians, so you're halfway around the circle, then you will double that angle to bring you to the full way around the circle. Okay, so then the periodic points of this thing, the periodic points, they are going to be points so that your pth power of theta is equal to theta, which is the same as saying theta is equal to 2 to the pth power times theta. And of course, this is taken modulo 2 pi here, right? So I should really have an equivalence relation here. But again, as I do this, it's kind of understood implicitly. And it turns out that all of these points can be characterized by using the periodicity of theta so that we know that theta is a period p point if and only if. So I'm going to leave this as an exercise for you to determine on your own. It's going to be 2 pi k divided by 2 to the p minus 1, where in my case, I'll just sort of write this off to the side. 1 is less than k, pardon me, because 0 will give me just the 0 point. Actually, yeah, we can use 0. 0 is less than k, less than 2 to the p. So that actually tells you a lot of information here. So with k equal to 0, that gives you just the origin on the circle, right? So your perfect 0 radians. That point is fixed for all iterates of the map, okay? So theta equal to 0 is a fixed point. Whereas For every single period p, there are a lot of sequences that repeat after p iterates. However, as I just mentioned, theta equal to 0, which is the k equal to 0 point, is already accounted for in every single one of these sequences. And that makes sense because a fixed point is also a periodic point. And that's why we start talking about prime periods, okay? So these are equidistributed over the unit circle, but only a few of them actually repeat after p, right? So as we go up with periods, you get more and more periodic points, but a lot of them have smaller prime periods, okay? Now, these are roots of unity. Let's actually look at another example here, right? I really want to sort of drill examples on us here. Let's go back to a real valued mapping x squared here. Then in this case, f of 1 is equal to 1, which implies x equal to 1 is a fixed point. Same with 0, but what I want to look at is f of minus 1 is equal to 1. And so the orbit, right, its orbit here looks like this. If I started at minus 1, it would go minus 1, 1, 1, 1, 1, and so on and so forth. So it is an eventually constant sequence. However, it didn't start at a fixed point, right? So in this case, then we would call this function a pre-periodic point. So x equal to minus 1 is a pre-periodic or prefixed point. Okay? So it maps into a fixed point. And another way of thinking about a pre-periodic orbit is a sequence that is eventually constant. Okay? That's how we should think about this thing. And we also can talk about a definition as we're going through this, because one way you can think about this is the orbit that starts at minus 1 converges to the fixed point at 1. With this notion of convergence, we can define what's called the stable manifold. Okay, so we can say that the stable manifold of a periodic point x is equal to all of the initial conditions such that the forward orbit, the limit, as let's use I goes to infinity. Actually, we can use n here. Let's not introduce unnecessary notation. Fn of x is equal, Fn of x0, sorry, is equal to x. Okay, so the stable manifold, so this is new nomenclature maybe. The stable manifold of a fixed point x, okay, is going to be all of the initial conditions that lead to orbits that converge to this fixed point, okay? So, for example, minus 1 belongs to the stable manifold of 1, okay? Of course, the fixed point itself belongs to the stable manifold. There is, again, for those of you that are coming at this with a little bit of knowledge of topology, there is a notion of the word manifold in here. I have not proven that this is a manifold. However, we can actually prove that this defines a manifold for the function. Another thing is, if this is invertible, okay, if f is an invertible mapping, we can also define the unstable manifold. And the unstable manifold is the set of initial conditions so that the backwards limit, f minus n of x0, is equal to x, okay? And that can only be defined whenever you actually have invertibility. So this one, is a little bit more complicated. We call this the unstable manifold. Stable manifold. And the reason for that is because you have to go backwards in time to arrive at the fixed point here. And this to the minus n notation, I know this is not 1 over. This is an inverse, and then I'm using the minus n to be the inverse composed with itself n times, right? So it's this definition just with the inverse here, okay? So be careful, try not to get too confused. I do apologize if this is a little bit confusing. However, this is very standard notation for chaos theory and dynamical systems in general. And so, I'm not going to abandon it. I know that it might be a little bit counterintuitive, but of course, as you start reading about chaos theory, you'll see this same notation, these same nomenclatures coming up over and over. And let's do some more examples here. Let's go back to this guy, okay? X cubed. Now, this is actually a one-to-one and onto function. It is invertible. It's continuously invertible. And that means that I can talk about forward and backward orbits. And I can also talk about stable and unstable manifolds. And we already analyzed it. We said it has 3 fixed points, one at 0, one at plus or minus 1. And actually, what you can prove is the stable manifold of 0. The stable manifold of 0 is actually the entire open interval between minus 1 and 1. So I'm going to leave that. We can actually prove this in the next lecture when we start talking about hyperbolicity. But I'm going to leave this for you to experiment with. What you could do is you could verify this numerically, okay? So you could randomly choose different numbers between minus 1 and 1, okay, on the open interval. And then you could iterate them forward, and you can see that they will converge to 0, okay? There is no unstable manifold of this. So we could say, the unstable manifold of 0 is just the fixed point itself. It's always worth pointing out or noticing to ourselves that these manifolds are never empty because they always contain the fixed point themselves, right? Because if I just start at the fixed point, then I generate a backwards sequence of the fixed point again, which is a constant sequence that converges. But other than that, there's nothing else in this manifold. Similarly, we could look at, say, the stable manifold of minus 1. And in this case, we can also find that there is nothing in this except for the fixed point. And that's because the unstable manifold is actually everything on the negative real axis. So this is actually all x less than 0. And then you can play the same game. You can do this for plus or minus 1. So for the unstable manifold of 1, this is just all of the positive numbers. And the stable manifold is just itself. Okay, so we'll learn how to classify these things as we go through this, but I want you to just pay attention to a couple facts, okay? The sum of the dimensions of the stable and unstable manifold in this case is the dimension of the full space. WS here, the stable manifold is 1-dimensional. The unstable manifold is 0-dimensional. 1 plus 0 is 1. This is a 1-dimensional mapping. The stable and unstable manifolds, 0-dimensional, 1-dimensional, full dimension is 1, and so on and so forth. The other thing that you can see is that these things are actually manifolds if that is a term that you are familiar with. Of course, knowing what a manifold is not critical to surviving this lecture series, so don't get turned off. However, this might be a fun opportunity to learn some new math. Now, we can also represent these orbits geometrically. So for example, let's think about a really, really simple function. Let's imagine we have f of x is equal to minus x, okay? So every time you get a number, you just negate it, okay? Then if we think about the number line here, right, where we are on the number line, if here's the middle at 0, what do the orbits look like? Well, if I started, say, at some positive number, I would jump with my orbit to the negative value of that. So let's say this is 2, let's say this is minus 2, but then I would just jump back. Okay, so now I can see that the orbit is just tick-tocking back and forth. Everything is a period 2 point except for 0, which is a fixed point. Similarly, I could start here, I would jump over, and then I would just come back. Okay, so not a particularly interesting mapping, but still one worth talking about nonetheless. So what if we did, say, f of x is equal to x cubed? Okay, well, we know that there are 3 fixed points, so we should start by writing those down. We know that these values sort of come back to themselves, okay? So this is my little geometric picture of my fixed points coming back to themselves. These are little loops that sort of cycle back. Then, if I start with a number, say, here, what happens is it remains positive, and it's a number between 0 and 1, so cubing it makes it smaller. So it actually just sort of jumps like this. And this is not to scale, right? But then they continue to jump, and you can see that it sort of jumps into 0. Same thing as if you started over here, stays negative and jumps into 0. While if you start with a number bigger than 1, then, so imagine 2, you cube that, it becomes 8. It goes way bigger. And then it just keeps hopping away. Same thing with minus 1, it hops away. So again, this is a visual process. You can see the stable manifold, everything between minus 1 and 1 collapses into 0. Whereas everything from close to 1 gets pushed away from it. And same thing, everything close to minus 1 also gets pushed away from it. Now, another thing that you can do here is draw a cobweb diagram. Now, I've done a few videos on cobweb diagrams already. I will put a link to that in the description of this video so that you can see how to do that. It's important to note that both cobweb diagrams and these little hippity-hopping visual descriptions here are only applicable to one-dimensional mappings. Okay, so we can rely on visualization for the early part of this lecture series, but eventually we have to rely on mathematical abstraction and a complete understanding of things in order to move forward. And let's take a look at one more or a couple more examples, again with the circle. So let's look at this example. So when I put theta up, it always means that I'm talking about the circle. Let's say f of theta is equal to theta. Okay, so it just takes the number, and then it adds, I'm going to say epsilon sine of 2 theta. And in this case, my epsilon is a small parameter that is going to be between 0 and 1/2. And if you want to have a little bit of fun, try and see what happens when epsilon is larger, if it's negative, all kinds of stuff, right? So this is a really fun dynamical system in order to try and understand. You can, again, iterate this on the computer. You just need to implement a modulo 2 pi condition as you're iterating forward so that you don't blow up. You need to stay in the interval 0 to 2 pi. Okay, so in this case, the fixed points, let's use a different color. The fixed points are essentially the roots of sine of 2 theta. So these are theta is equal to 0, theta is equal to pi over 2, theta is equal to pi, and 3 pi over 2. And of course, there's only finitely many of these fixed points. This should be a theta. And that comes from the fact that, you know, we're only talking about theta between 0 and 2 pi here, right? And so what we can also check out here is if we take a look at this mapping, and I'm going to use the ideas for here in a second. If I take a look here, I can see that f prime of 0 was equal to 0, whereas f prime of plus or minus 1 is equal to, so here now I get 3. Okay? Now, something that we can take note of here is this number is smaller than 1, as we're going to talk about in the next lecture series. But because it's smaller than 1, it means that things are contracting, right? So lengths are becoming smaller, whereas here, this value is larger than 1, so lengths are getting larger. So let's actually try and use the same thing here, because this tells us that everybody collapsed into 0, at least nearby, and this told us that everybody gets pushed away from plus or minus 1 nearby. So let's take a look. Let's do f prime of pi over 2, and this is the same as f prime of 3 pi over 2 as well, okay? And this comes out to be 1 minus 2 epsilon, okay? And because I'm restricting epsilon to be between 0 and 1/2, this is actually a positive number that is less than 1. So it says that nearby, lengths of things are collapsing, they're getting smaller. So it should be indicating to us that we move close to these points when we start close to them. Whereas f prime of 0 and f prime of pi, in this case, is equal to 1, and then plus epsilon, plus 2 epsilon, pardon me, 1 plus 2 epsilon, which in our case is bigger than 1, which tells us that we should be moving away. So what we can do is we can do a visual representation of this. Here's my circle. Honestly, not the worst circle I've ever drawn in my life. 0, pi over 2, 3 pi over 2, and, pi, pardon me. I got excited, and 3 pi over 2. And if you start putting things into your calculator, you can see that if you started here, for example, you would be being pushed down like this. So I'm going to use these little arrows to show you where you're going. So if you started close to 0 below it, you would be pushed down to 3 pi over 2. If you started below pi here, you would be pushed down to 3 pi over 2. If you started above, you would be pushed up. And again, you can get this feeling from just doing simulations with random initial conditions, right? And sort of plotting where they wind up. Now, these conditions right here, as we'll see in the next video, actually quantify this perfectly and tell us that because everybody gets sucked into this like it's quicksand, we're going to call this thing stable, and this is a condition that tells us that it's a stable fixed point. Whereas, because everything gets pushed away from pi and 0 like they're the top of a mountaintop, these are called unstable, and again, this condition right here tells us everything we need to know. So, in fact, you can have basically the same thing, but you can augment this. And I'm going to leave this as an exercise for you. Here's the map that you can play with to try and get some information out of. Theta plus epsilon sine of n theta. And in this case, epsilon has to be between 0 and 1 over n. So the example that we had right here was n is equal to 2. I want you to try and work through this on your own. Find the fixed points, classify them as stable or unstable, and draw a picture just like I did right here. I think that that's a good exercise. Another thing that I want you to also try is take a look at what happens when epsilon becomes negative here, or what happens when epsilon moves outside of this interval. Okay? And again, you can do these things through computation as well, right? The way that I start analyzing a dynamical system, if I don't know where to go with pencil and paper, is I program it up. Okay, when we come back in the next video lecture, we are going to actually quantify what it means to be stable and unstable. We're going to talk about these conditions more and how it helps us understand the stable and unstable manifolds of fixed points and even periodic points. So I'll see you all in the next video, everybody.